Thanks, Mark. And thanks so much for having me here. So, we have heard a lot over the last couple of days about how to build quantum computers, how to control quantum computers. We heard a little bit today about applications. But there is this kind of well-known secret that there is a global community trying to figure out what to do with these systems. And I've recently been thinking about alternative ways to figure out how we might leverage these systems to do something interesting. And I somehow found myself falling back into game theory, which, as Mark noted, is already used in a lot of different areas. And so what I want to do today is kind of talk a bit about what I've been thinking about. This is not new, novel research. Rather, what I want to do is impart on a DEFCON audience the tools that would let you start thinking about quantum game theory as a, I believe, underappreciated way to start thinking about the applications of these systems. I say I believe underappreciated because I think there are not enough people doing it. I may be wrong about that. But I can say that I have been recently vindicated because there was a paper that went up on the archive about a week and a half ago talking about how you can use certain quantum games to do certain interesting tasks like high-frequency trading and stuff. So it is starting to get some attention perhaps, but there's still a lot to do here. So I will be throwing a fair bit at you along the way, partially because I want you to, as I said, be able to go and start looking at some literature and at least get a sense of what's going on. But what we're going to do is walk through some of the fundamental results from early on in the quantum game theory literature back 25 years ago now. So who am I? I'm Mike Dascal. Very briefly, I believe I have the coolest title in my company. I'm Director of Quantum Product Management. And I'm at the Fidelity Center for Applied Technology, which is a research and innovation hub in Fidelity. Specifically, I sit in the, is this going to work? Almost. Where's the other screen? I sit in the quantum and future computing team, which has as its mission, I can't seem to get my clicker to work. Anyway, doesn't matter, I'll just stand here, I guess. We see as our mission to prepare Fidelity for advances in computing. So, okay, I'm not going to talk about Fidelity. I'm going to talk about quantum game theory. We're going to start with a bit of an intro to quantum computing, which I know we've seen a couple of these in the past few days, but there are those who are just joining. We're not going to do a lot of quantum mechanics, but you need to know a little bit, right? So first of all, our pieces of information in quantum mechanics are quantum bits or qubits. We think of them as, at least when we measure them, being in a 0 or a 1 state. So a quantum qubit is in a state that's represented by a two-dimensional vector. We have a 0 state we define as 1, 0, a 1 state 0, 1, and we can put these things into what we call superpositions, which are just linear combinations of 0 and 1. For example, alpha 0 plus beta 1, or alpha beta. And when you have a state when you have a system in this state, when you measure it at the end, you're going to get either a 0 or 1 with the probabilities of modulus of alpha squared or modulus of beta squared, respectively. Now, if you have a bunch of qubits, they are also represented by vectors, and the dimensionality of these vectors grows with the number of qubits involved, so by 2 to the n. So for example, 2 qubits are going to be in a 4-dimensional vector. If each of these qubits is in a state alpha 0 plus beta 1 and gamma 0 plus delta 1, this is what your vector looked like. It's a tensor product. And you can again read off probabilities. So the probability of measuring these 2 qubits and getting a 0, 0 in this case is going to be alpha gamma squared. But the number of vectors that look like this is much larger than the number of vectors that look like this and can be split up. So there are plenty of vectors that you can't separate like this. These are called entangled vectors or entangled states. An example of this would be 1 over root 2, 0, 0 plus 1 over root 2, 1, 1. So we've got a 1 over root 2 here, and then 0s in the middle. And if you have qubits in that state, the chances of getting a 0, 0 is 1/2, 1 over root 2 squared. Similarly for 1, 1, and the chances of getting a 0 and 1 and a 1 and 0 are 0. Importantly, you can't take that and separate it out into 2 states like this. That's what makes it entangled. In addition to our qubits, we have quantum operations, quantum gates. Here are 3 examples. So for example, a NOT gate will take a 0 to a 1 and a 1 to a 0. Importantly, when you operate it on a state like alpha 0 plus beta 1, you put the NOT in front of it, it operates linearly. So you'll end up with the 0 switching, so you have alpha 1, the 1 switching, so you have beta 0. And that's true for all quantum gates. They're going to operate on each segment of the superposition. We have gates like Hadamard, which take our 0, put it to a superposition of 0 and 1, 1 over root 2, 0 plus 1 over root 2, 1, or it takes 1 and put it to 1 over root 2, 0 minus 1 over root 2, 1. It's worth noting the probabilities here of measuring a 0 and 1 are the same. 1 over root 2 squared is the same as minus 1 over root 2 squared. But that minus is important when it comes to quantum states. This is the type of thing that gives us quantum interference. The Hadamard is also its own inverse. And importantly, every quantum gate must have an inverse. This is a rule of quantum mechanics. Everything has to be reversible. We also have gates over multiple qubits, like C0. We've already seen a couple of these today. So this will operate such that if the first qubit is in a 0 state, nothing happens to the second. If the first is in a 1 state, the second one switches. And again, if you have a superposition of two qubits, like this one, alpha 0, 0, beta 1, 1, etc., it applies on each term in that superposition. Now, I have gone through this quickly, partially because I imagine some of us have seen it a couple times in the last day and a half. But it's also relatively simple for what we're going to need to do today. Thinking about quantum games, there are also two kind of quantum rules that I think are worth highlighting right off the bat. The first is no cloning. I know we haven't talked about quantum games yet, but still, there are these quantum rules that I think are important to keep in mind if you go out and start thinking about what a quantum game might look like. No cloning says that you cannot have any operation that copies an arbitrary quantum state. And it's really easy to prove that that's impossible. So here's what we'd want. We want some operation U that's going to take a qubit in some state psi and some qubit in some ready state R and just make two copies of it. Well, let's assume we can do it for 0. So 0R goes to 0, 0. Let's assume we can do it for 1. So 1R goes to 1, 1. Well, then if we try to apply it to some quantum state alpha 0 plus beta 1, what we're going to get, because it's going to apply on each term, is an alpha 0, 0 plus beta 1, 1. And if you kind of do the math, or you might be able to see off the bat, this is an entangled state. So the qubits in here don't have their own state, right? This vector looks like this. Whereas if you wanted each qubit to be in that alpha 0 plus beta 1 state, you would end up with a vector. This is what you're looking for. So this can't happen. This is just a rule of quantum mechanics. You cannot have an operation that copies an arbitrary quantum state. Another rule that I'm not going to go over formally, I don't know if I could if you asked me, if I'm being honest, is the no signaling rule. This says that, despite the fact that we have these entangled states, which many of you probably know, they behave in a fashion, they exhibit correlations that are stronger than anything you could do classically. Despite that fact, you can never use these things to send a message from one of these qubits to another, to signal at all. So if Alice and Bob share qubits in this state, alpha 0, 0 plus beta 1, 1, and here this is just saying Alice has this qubit, Bob has this one, Alice has this one, Bob has this one. On either end, and let's say they take their qubits, Bob goes out to Alpha Centauri, Alice stays here. For both of them, when they measure their qubits, they are going to measure 0 with alpha squared probability and 1 with a beta squared probability, and that's all they're going to see. There's nothing Alice can do on her qubit to change that on Bob's end. And in fact, moreover, Bob will never know whether or not Alice has even measured her qubit. And I'm not even talking about the difficulties of that statement when we think about special relativity. This is just like, you cannot do anything to send messages with quantum systems like this. So, okay, that's all the basics of quantum mechanics we're going to do. I think that's all you need to go over these fundamental results. It might look a little bit messy later on, but it won't be too bad, and it'll simplify really easily. So let's talk about games. Here's an archetypal game that many of you probably know, Prisoner's Dilemma. Story goes, you have prisoner A, say Alice and Bob. Alice and Bob are everywhere, right? Alice and Bob have committed some crimes. The police know about a minor crime. They have very strong beliefs about a major crime. And they tell to Alice, and I guess to Bob as well, if you confess, then Bob doesn't, you're going to walk free, Bob's going to get put in jail for 20 years. What they don't tell Alice is, first of all, that they've said the same thing to Bob, perhaps, but also that if they both confess, there's no deal to be struck, so they're both going to get locked up for 5 years. They also don't tell them that they don't really have evidence of the strong crime, they only have evidence of the small crime, so if they both just keep quiet, they're only going to get locked up for 1 year each on that small crime charge. So the difficulty here, and we're going to talk about this slightly more formally later, is that rational players, and I'm going to put this in scare quotes because, this is I guess a foundational belief or foundational move in game theory, is you treat your players as these perfectly rational agents that can do all the math they need to do immediately in their head. They know, magical things. Put that aside. That's just part of the rules of game theory. Perfectly rational agents in this situation are going to end up here. And that's a bit of a problem because there's a clear winner, right? And again, we're going to go over that a little bit more formally later on. I just want to introduce games and some terminology here. Now, this is a story that's often told. I want to translate this a little bit into a more game theoretic friendly version. And that's because the thing is, in game theory, we talk about payoffs. So players get payoffs when they, at the end of the game. And when it comes to payoffs, bigger numbers are usually better. So this is not a good way to think about things. So we're going to go to this version. So here we have Alice and Bob. They either cooperate with each other, in which case they only get smaller sentences, so they get a relatively good payoff of 3. If they both confess, they're both locked up for 5 years, so it's not a great payoff of 1. But let's say Alice confesses, so Alice defects from the cooperation, and Bob stays quiet. Well, Alice gets a payoff of 5 because she's walking off free, whereas Bob is getting no payoff. He's stuck in jail. It is worth noting these numbers kind of do matter. So I've picked these because they're used in kind of a couple papers we're going to look at. But when it comes to calculating expected payoffs, these can come into play. We're not going to talk about that too much, but it's just something to be aware of. So I did mention earlier, I will be throwing a few things in here, like terminology, some concepts, because I want you to be able to go and read a paper and say, oh, okay, I know what that means. So first of all, some terminology with these games. I've already mentioned a couple of this. So we have our players, Alice and Bob. Alice and Bob each have strategies. In this case, the strategies are defect and cooperate. In this type of game, they're making one move. They're making it at the same time. Strategies, more generally, can have multiple moves. We're going to look at a case like that in a second. We have our payoffs. The convention here is the first number is our rows. The second number is our columns. And this whole thing is called the game in normal form. You can have games that have more players, so you have a higher dimensionality of this matrix. You can have more moves. But when you have a table like this, that's a game in normal form. It's not always great to represent a game in normal form, and that's a nice way for me to introduce our first quantum game. And when I say our first quantum game, I don't just mean the one that we're going to look at. I also mean what I believe is the first quantum game. This is a paper I recommended, written by Meyer in '99. I'm going to use Meyer's story because it's a great story. So this is called the quantum penny flipping game. We're going to start with the classical version. So classically, the Enterprise is being held hostage by Q. And Q says to Picard, we're going to play a game, and here's how it's going to go. We're going to put a coin in a box heads up. I'm going to put my hand in the box and flip the coin or not flip the coin. Then you're going to put your hand in the box and flip the coin and not flip the coin, not knowing what he'd done, right? Then Q's going to go again, put his hand in the box, flip the coin or not flip the coin. Then they're going to open the box, and if the coin is heads up, Q wins. If the coin is tails up, Picard wins. The Enterprise goes free. I don't know what happens if Q wins. Doesn't go into those details. Now, first of all, again, to introduce some terminology for you. This representation, I should say, you'll notice I don't have numbers here. I have the letters representing the winners. That's because this is a game, a zero-sum game, a game where when one person wins, the other person loses just as much. But note that here the strategies have multiple moves. There's a lot going on. It's not all simultaneous. There's a chronology, and so that's often depicted in a game in extensive form. The extensive form not only tells you about what's going on at each move, but you also have these lines that indicate players who don't know what's going on. So Picard, after Q has gone, Picard doesn't know whether the game is in this state or in this state. Now, looking at this, well, both the table and the extensive form, it becomes pretty clear that Picard doesn't have a great strategy here, right? If he chooses to flip the coin, he's going to win half the time. If he chooses not to flip the coin, he's going to win half the time. There isn't much that he can do to make that any better. Importantly, we can also introduce probabilistic strategies or mixed strategies where you might say, okay, let's say Picard has a quantum random number generator, and he's going to use that to determine whether he flips or doesn't flip. It's not really going to help too much here either, but it is an important concept that we're going to see again in a second. So at first glance, it looks like Picard should be winning half the time, as should Q, right? Needless to say, they play the game, Q wins. Picard says best 2 out of 3. He goes, okay. Play again, Q wins. Picard says, okay, best 3 out of 5. Play again, Q wins. Seeing a pattern here. And the pattern is Q is Q. And so Q is not playing the classical penny flipping game. Q is playing the quantum penny flipping game. So what we're going to see is that if we represent this game in a quantum space, and we let Q make quantum moves, this explains how Q is winning at every round. We're going to start by saying, OK, let's call the coin in the heads-up position H, which is going to be our 0 vector. When it's tails, it's going to be 1, which is our 1 vector. And then we can define our moves as quantum operations. So flipping is just the NOT gate. It's turning a 0 to a 1 and a 1 to a 0. And not flipping is just an identity matrix. It doesn't really do anything to the vector. Well, here's the thing. This is what Picard's doing. He's picking between these. Q is doing this thing here, which is our Hadamard gate that I mentioned earlier. So let's see how this works. Right? So we have a game that has the initial state, then Q goes first time, then Picard goes, then Q goes. So Q is going to play his Hadamard move for both the first and the third. And a little bit of simple matrix algebra here. So we start with, I'm going to pull my 1 over root 2, so we just have some 1s. So we have Hadamard on 1, 0, which gives us 1, 1. If Picard flips, well, the NOT gate is going to work on each part of that superposition. So the heads part goes to tails, the tail part goes to heads, and we have the same 1, 1. Well, then Hadamard's going to be applied again, and we saw that Hadamard is its own inverse. So we end up with a heads at the end of it. So Q knows that if Picard flips, the coin is going to be in the heads position. Q also knows that if Picard doesn't flip, the coin is going to be in the heads position. And it's the same simple math. So we have the Hadamard on the 1, 0, which gives us 1, 1. Now, if Picard doesn't flip, it's an identity, so it's still 1, 1. We applied Hadamard again, and we end up in heads again. So by letting Q make this quantum move, he's changed his 50-50 probability to 100%. And it is worth noting that if we do introduce those mixed strategies that I mentioned, this doesn't change anything. So now we have a mixture, like a probabilistic mixture of Picard flipping or not flipping. Well, we have a probability of it landing heads plus 1 minus that probability of it landing heads. It's going to land heads. For those that know, I'll just mention, yes, we should be doing this with entity matrices. We're not talking about that here. Now, so this is it's a relatively simple case, but like we've already seen that the introduction of these quantum moves can really change the outcome of a classical game. There are some further results from this paper that are worth highlighting, kind of in the context of quantum game theory. So first of all, penny flipping is a game, I mentioned this already, it's a zero-sum game. When one player wins, the other player loses. Now, there are some important results about zero-sum games historically, and as well some non-zero-sum games. So it was proven back in '44 by von Neumann and Morgenstern, who I think wrote the first game theory textbook, that when you have quantum games, you end up with these equilibrium strategy mixes, these combinations of strategies where players would not do better to change, right? Knowing that another player, or believing another player is using strategy A, if you're using strategy B, you're not going to do better by changing that. This was generalized a little bit by John Nash to form what's called a Nash equilibrium. John Nash, you might have heard of him. He won a Nobel Prize in economics, I believe, for this. And what he shows is that indeed any game where you allow those mixed strategies has these equilibrium points, these points where when the players are using certain strategies, they're gonna rationally land there because moving away would not do them better. In the classical penny flipping game, there is a Nash equilibrium of just doing a 50-50 split. That's because if one person isn't doing a 50-50 split, you can kind of do better by knowing whether or not they're going to flip or not. But of course, the equilibrium in the quantum case is, well, Q's going to win. He's not going to do any worse by doing if he does anything else, he's going to do worse. So that's that. But I don't raise this because I really want to focus on the concepts. There's more of a bigger picture here. There are some other results from Meyer that are worth highlighting. So first of all, Meyer shows from this that in general, if you have a game and you have one player using his classical moves, another player who's given quantum moves, the player with quantum moves is never going to do worse. You can only do better by having access to quantum moves. And it's not hard to see that, right? We saw earlier how we encoded our classical moves of flip and not flip into the quantum system. It's the same. That's generally true. You can encode the classical moves in the quantum game. So you're only expanding the space of possible moves when you give access to that. The other things that he proved, which I'll just mention quickly. I'm aware I'm running low on. I'm already behind time. He showed that when you have a zero-sum game, if both players have quantum strategies, there may not be an equilibrium. this is the same as in the classical case. You need to have those mixed strategies to get the equilibrium. And more importantly, he showed that if you have the mixed strategies, if you do have a probabilistic mixture of quantum strategies, you do get the promise of an equilibrium. So why am I saying this? It's not so much because I want to focus on what an equilibrium is or isn't. Rather, the important message here is that what Meyer shows is the introduction of quantum moves doesn't change the foundations of game theory. We're still working in the classical game theory structures and goals. So classically, you're looking for these equilibria, you're promised they're there in the right circumstances. That's still true in the quantum space. And that means that we can still take our old practices from traditional game theory and continue to use those to find the analogous cases in the quantum context. So, okay, that was game one. We're going to go through 3 games. The second game is really quick. We're going to, well, traditionally this game is called Battle of the Sexes. This is 2024, so we're going to call it Battle of the Hackers. This comes from a paper just after 99. And I should say, these are the early papers, right? There has been a tremendous amount that has followed, right? This is, we're just going through some of the fundamentals here. So in Battle of the Hackers, we have Alice and Bob. Alice wants to go to the Quantum Village. Bob wants to go to the biohacking village. Both Alice and Bob want to hang out together. So the payoff, our normal form here says, if they end up together at the Quantum Village, Alice is going to get a 5 payout. Bob's only going to get 3. He'd rather go to biohacking. If they're both in biohacking, Alice only gets 3 because she'd rather be in quantum. Bob's going to get 5. But they really want to hang out together. If they're not in the same space, they are not happy about it. Now, classically, there is an equilibrium. There are 2 equilibria, actually. So if they're both playing Q, or if they're both playing B, quantum or biohacking, so an equilibrium, Nash equilibrium is saying, I wasn't very clear about this. It's a strategy such that knowing what your opponent or your other player is doing, you are not inclined to leave. So if Alice knows that Bob is playing quantum, she's not going to do better by playing something else other than quantum. If she knows that Bob is biohacking, she's not going to do something better by not playing biohacking. And obviously, this is symmetric. So quantum and quantum, biohacking and biohacking are the equilibria strategies here. But we don't have a unique one, of course. Now, in the quantum case, this is a really quick quantum game, as some of you might have already kind of figured out. We're not going to use quantum moves. That's a little bit unnecessary. That should say moves for reasons you're about to see in a second. We're going to give them a pair of entangled particles. We're going to say, okay, Alice and Bob can share a pair I say particles, I should say qubits, sorry. They're going to have a pair of qubits in the 0, 0 plus 1, 1 state. They're going to agree. Let's imagine, they're waking up in their hotel rooms and their phones are both dead. So this is the only way they can plan. And they can't communicate with us. So when they measure their qubits in the morning, if they get a 0, they're going to go to quantum. If they measure 1, they're going to go to biohacking. What we know is that they're going to end up in one of those 2 corner cells where they're both getting positive payoffs. They're not going to end up in their negative, in the 0, 0 cases. So this is a really simple quantum game in a sense. But I wanted to raise it for 2 reasons. First of all, it is an early one. The other one is that it does kind of introduce a slightly interesting note, which is that we're treating this as giving Alice and Bob quantum resources to coordinate what they're doing. And that's a perfectly fine way to think about it. But it's also worth noting that this is isomorphic to having quantum strategies, by which I mean, I should have used the word moves here, right? If we think of what Q did in the last example as using a quantum move, putting the game in a quantum state, here what we have are quantum strategies that are themselves entangled. So Alice and Bob's strategies are coordinated in this fashion. And it's interesting to note that in the quantum game theory literature, these are both possible, and they can both provide advantages. I'm willing to say that it's generally true that having quantum strategies is equivalent to giving quantum resources in this sense. And they're both, I highlighted that because, again, as you go out, if you're interested in this and want to think about building quantum games, whichever way helps is fine, right? These are, I believe, isomorphic. I was going to say one more thing and I've forgotten what it was. It'll come back to me at the end, I'm sure. So we have, so we have our quantum moves. We have our quantum strategies. The last thing I want to talk about, the last game I want to talk about, is I'm going to kind of put both of these together, and I think it has the biggest punchline in a sense, and that is back to the prisoner's dilemma. So the prisoner's dilemma, I mean, it's a pretty famous game because it's got a very formally a very simple problem, which is that the players are going to end up here. Now, why are they going to end up here, formally speaking? It's because of what we call dominant strategies. So a strategy is dominant if no matter what the other player does, you are not going to do any worse by, you are going to do at least as well staying where you are. It's at least as good as. We also have strict dominance, which says that regardless of what another player does, you will do better playing that strategy. And in this case, in the case of the prisoner's dilemma, defect is the strictly dominant strategy for both players. So if Bob, think your analysis point of view, if Bob cooperates, well, either you're going to defect and get 5, or you're going to cooperate and get 3. So better to defect. If Bob defects, well, if you cooperate, you get 0. Better to defect. So you have two players who have strictly dominating strategies that push them into this equilibrium that is often called an inefficient Nash equilibrium. It is a Nash equilibrium, but it's a bad one, right? They're both doing pretty poorly here. Now, this was addressed in another paper in '99 in, like I said, this fashion that I think, I don't know, to me it's the biggest punchline in quantum game theory from these fundamental papers. There's been a lot of work enriching this literature, specifically in the prisoner's dilemma, the quantum prisoner's dilemma. We're going to just go into the basics. And the math will look a little bit scary for a second, but I promise you it's not so bad. So we have Isert, Wilkins, and Lewinstein in '99. You can check out their paper. And what they do is they put the entire game into a quantum system. So they say, okay, let's imagine our game is a 2-qubit system. So we've got 2 qubits. We're going to define states C and state D as 0 and 1 respectively. Don't necessarily think about these as strategies, but rather as together indicating what combinations of payoffs you're going to get. So if the game is in the CC state at the end of the game, you're going to get payoffs of 3 and 3. They then say, okay, so we can describe the game as this 4-dimensional vector composed of our 2 qubits here. And at a time t, it can be described, generally speaking, as some superposition of CC, CD, DC, and DD. They then go on to show, I'm not going to kind of get into the dirty details here, but they show the whole game could be described as this thing here. So what we have here is the initial state of the game, CC. We have this 2-qubit matrix J. We have Alice's and Bob's strategies forming we have a 2x2 by a 2x2. We have a 4x4 matrix here. And then the inverse of this J. So again, bear with me. It's going to look messy. We're going to get better. They then say, okay, we can generally describe the strategies of Alice and Bob in this parameterized fashion. So they're going to be these 2x2 matrices parameterized by theta and phi, looking like this. And when you have theta and phi both being 0, we have our cooperate. Cooperate strategy, which is just an identity matrix. Nothing happens. Then we have our defect strategy, which is when theta equals pi and phi equals 0, which they define like that. They then say, given these, and given that what they want is to make a game wherein you do retrieve the classical game when the values are set correctly, right? They say, okay, J has to have this form. Okay, what is this thing? It's a mess. It looks even messier if we, I should mention, they're using the capital C's here for the operations, the little c's are for the states. They have a little, I changed it a little bit, but I know it's a little bit messy. I want to follow roughly their notation. But yeah, so we have this messy looking thing here. If we spell it out, it looks like this. It's even scarier. And what the J is doing here, so you know what these things are doing here. These are the Alice's strategy, Bob's strategy, and they will simplify. What the J things are doing here are introducing entanglement between the Alice and Bob qubits in this game. And they parameterize it so that you can say, okay, that entanglement, we can introduce full entanglement or no entanglement. And when there's no entanglement, it should look like a classical game where the Alice and Bob aren't entangled. So there are kind of both types of quantum introductions happening here. We have this thing, which is entangling Alice's and Bob's qubits. So it's like giving them entangled qubits. And we have these things, which are putting in quantum moves. Alice and Bob are not just playing classical moves in a coordinated fashion. They're actually putting the game into quantum states. And you might say, okay, why are we doing all this? Well, let's take a simpler case. So let's begin by looking at what happens when we do have that maximal entanglement. We're not going to worry about when these things aren't entangled. So we're only going to take cases where we have Alice's and Bob's qubits being maximally entangled. These two matrices look like this. Don't worry about that. What you should focus on is the fact that this is like a 2-qubit Hadamard gate. It's going to take, if we look at this here, so this is our initial CC state. It's going to take that CC state and create a superposition between, in this case, CC and DD. This is then going to undo that. And what we have in the middle are what Alice and Bob are going to do. So when Alice uses strategy D, defect, and Bob uses strategy D, defect, even if they're entangled, it shouldn't matter. They should end up in the defect-defect state, right? That should just be what happens. And indeed, if you do the math here, hopefully it doesn't look too messy to you, right? We've got pretty simple matrices. You could even take out the 1 over root 2 from both of these, and they even look simpler. You begin in the CC state. You end up in this vector here, which does correspond to that DD state. So they both defect. Regardless of whether or not they're entangled, they're going to be in the defect-defect position. But what if Alice, or Bob rather, plays a quantum move? In this case, Q. Q is defined like this, and we're using I, if you hadn't, so these are complex numbers, I is the square root of -1. Well, same thing with our J's haven't changed, but now we have this matrix here in the middle. We apply it all to CC, and what happens now is we get this vector popping out, which corresponds to CD. Think about this for a second. Alice has played defect. Bob has played this quantum move. The result that pops out is what should happen only if Alice were to cooperate. So much like before, giving one of these players quantum moves allows for an advantage, right? Bob has essentially forced Alice to cooperate even though she hasn't, which is weird. The authors go on to actually prove that this Q move turns into a new equilibrium, a new Nash equilibrium. And when both players use it, the game ends up in, oh, my numbers have changed. They end up in the good case, the case where they both stay quiet, CC. I think I've misordered something in the earlier slide, but yeah, they end up in the CC state. So again, what this means is that giving players these quantum resources have let them get out of this really bad situation classically, where they have these dominant strategies that force them into this bad case, right? It forces them typically into the defect-defect case, where they're, I mean, in the old version, they're put in jail for 5 years. This lets them get into the case where they're only both locked up for 1 year, something that is otherwise unobtainable if they're rational players in a classical scenario. I'm going to finish up in just one note. So the context of this was, again, that I think this is a somewhat underappreciated way to start thinking about applications of quantum technologies, both computing and quantum communication. It is worth pressing that everything that happens in these discussions is directly translatable to quantum circuits, right? So this is our quantum prisoner's dilemma solution. We have our J, we have Alice and Bob doing their strategies, we have our J dagger. This needn't be all happening in the same place, right? If we have good quantum communications, this qubit can go very far away to Alice and then come back. So this could be an actual communication protocol. And so we have this new way to think about, okay, given that we have these resources and these abilities to create entangled states, to perform quantum operations, can we get out of these places where we're stuck in classical scenarios? again, this was just kind of the tip of the iceberg, right? So I really hope that, there are at least some of you out there who kind of walk away saying, okay, yeah, look, I have enough now. I can go read a paper and say, okay, I can start on this path. Happy to talk about it further, of course, but I don't expect everyone to get every concept that I just kind of mentioned here. There was a lot that I threw at you. But as you do go out, think about how this can apply, right? If I'm right, there is a tremendous opportunity here to find new applications, especially for quantum communications, by looking at things that we're doing today and thinking about what they would look like in a game theoretic case, and then saying, okay, what if we could do new types of move? What if we enriched our move space well beyond what's available classically? I went through that quicker than I thought I would, but thank you very much.
All right, we do have a little bit of time, I think, for some questions, if you're willing, Michael.
Yeah, absolutely.
Anyone want to come up and give a question, perhaps? An idea, a thought, a chance to hide? You just come up and join me, my friend. Don't worry, we'll wait. We are here for you. All right, keep it on your chin, please.
I have a question.
Close, yeah.
Okay, so I have a question about kind of deterministic games and classical like game theory. So when you apply when you introduce quantumness to like a game, I feel like you lose information. Like you no longer have perfect information between both players. So is it possible to have like a quantum game that is still deterministic in that classical sense?
So I might be misunderstanding, but in fact, the cases we saw here, we're using quantum strategies, but the outcomes are still deterministic. Or they're non-probabilistic, right? So if we go back, for example, to to this case here, these are quantum moves. But if you create your entanglement gate like this, and you begin in the C state like this, you will end up in a CC state at the end. So does that, I'm not sure if that answers it, but so I guess what I'm saying is the introduction of quantum moves doesn't necessarily introduce stochasticity or probabilistic outcomes. It can, and it is an important piece that I didn't really talk about here, that in traditional game theory, we think about expectation values of outcomes, right? So you say, well, a player isn't sure what output you're going to end up with. You don't know, Alice doesn't know what Bob's going to do, so Alice puts probabilities, maybe realistically, on whether Bob is going to confess or cooperate or defect, and then using those probabilities, weigh the possible payoff she's going to get. That would still be true in the quantum case. In the quantum case, we still have probability distributions over the possible outcomes, and can use those to calculate expectation values of payoffs. Does that answer? Yeah.
Thank you.
Excellent question. Any other questions? Come down, sir. Don't worry, my friends. This is all for our recordings. Everything will be on YouTube. All slides will be uploaded onto GitHub or something similar. No. Oh, he didn't want to ask a question. He just buggered off. Okay, fair enough. I've had the same reaction to myself. Any questions from the audience at all? Yes. Evan. Beatbox yourself.
So I don't know too much about sort of adversarial artificial intelligence, but it seems like it might relate to game theory. And do you know if there's any sort of quantum adversarial generative networks or anything of that form that would be a quantum equivalent?
Can you repeat the question?
Yeah, so I guess the question is whether there's something analogous to an adversarial AI case in the game theoretic context. I guess I don't know. I think you could probably build one. I think it does depend on how the AI is being adversarial in a sense. But generally speaking, right, these are very simple games that I've just described here. They can get much more complex with many other players. with different types of desired outcomes. Players that want to coordinate and cooperate, and ones that want to compete. And you have games where you have multiple players coordinating to compete against nature, or perhaps an adversarial AI. So yeah, I mean, I guess I feel like there should be, the answer should be yes, but I don't know.
Brilliant. All right, if there's no other questions, please thank Michael again.